Good afternoon. Today's lesson is part 2 of the acid-base lecture series. In this lesson, we will be calculating the pH for both strong and weak acids and bases. In this video, the student can, based on the dependence of Kw on temperature, reason that neutrality requires H plus to equal OH minus concentrations, as opposed to requiring a pH of 7, including especially those applications to biological systems. The student can identify a given solution as containing a mixture of strong acids and or bases and calculate or estimate the pH and concentrations of all chemical species and the resulting solutions. And the student can identify a given solution as being the solution of a monoproduct weak acid or base, including salts in which one is a weak acid or a base, calculate the pH and the concentrations of all the species in the solution, and or infer the relative strengths of the weak acid or base from given equilibrium concentrations. We're going to begin with the autoionization of water. This should be a revisiting of what we learned in our first video, but you have two water molecules that, when they come in contact with each other, have the potential to form H3O plus and OH minus ions. Essentially, what is going to happen is one of the hydrogens off of one of the molecules will basically cleave off, leaving the two lone pair electrons, and this will form a bond with the lone pair electrons on the oxygen on the other water molecule. So what you form is the H3O plus, again a coordinate covalent bond, and then you're left with the OH minus ion as well. Now, like we said, this happens in a very small amount. The water will slightly dissociate into the ions at equilibrium, known as a process of autoionization or self-ionization. When this occurs, the concentration of the water will break down into 1 times 10 to the negative 7th molar H3O plus and 1 times 10 to the negative 7th OH minus when we are at 25 degrees Celsius. If the temperature changes, that value for the K will change as well. It is an endothermic process, so increasing the temperature will cause a greater degree of H3O plus and OH minus to form in solution. So for the water equilibrium system, we have two water molecules forming the H3O plus and the OH minus. The equilibrium constant Kc would be equal to the H3O plus times the OH minus divided by the H2O squared. Remember though that since the water is a liquid, it is a constant, so we'd remove that from the equation, incorporate that with the value for Kc, and that leaves us with the Kw being equal to the H3O plus times the OH minus to equal a constant 1 times 10 to the negative 14th at 25 degrees Celsius. So no matter what the solution is, think about Le Chatelier's principle. Anytime that we have an acidic solution, as we had mentioned, the H3O plus is greater than the OH minus. They're still going to end up multiplied together, equaling the 1 times 10 to the negative 14th. But you can tell if I have a larger concentration of H3O plus, then my OH minus concentration would have to drop in order for them to still equal 1 times 10 to the minus 14th. In the pure water, again, 1 times 10 to the minus 7th. That's why we normally say that neutral solutions have a pH of 7. We are, of course, approximating that it is 25 degrees Celsius when we are making that assumption. But both of the ions are always going to be present in all aqueous systems. So you always have the H3O plus and the OH minus present in any solution that you would be creating. So according to Le Chatelier's principle, a change in the H3O plus causes an inverse change in the OH minus and vice versa. So if I have a higher H3O plus, I'm going to have a lower OH minus, higher OH minus, lower H3O plus. We can define the terms acidic and basic in terms of comparing the concentrations of the H3O plus and the OH minus ions. If my solution is acidic, then my H3O plus is greater than my OH minus. If I have a neutral solution, I have equal amounts of H3O plus and OH minus. And then if I have a basic solution, H3O plus would be less than OH minus. I want to stress again, especially when we're talking about the neutral solutions, temperature is a huge factor in that. So pH is only 7 for a neutral solution when the temperature is at 25 degrees. If it is 60 degrees Celsius instead, then a neutral solution might occur somewhere around 6.3. So it is very much a temperature dependent system. We're now going to begin our look at calculating pHs. pH stands for the negative log of the H plus or H3O plus concentration. They can be used synonymously with each other. When we look at the negative log, the P that we see here, that is the negative log. So you can take the pKa, you can take the pKb, the pKw. There are a bunch of those different ones that you could choose. Those are all meaning the negative log, and then you can just fill in the blank for that. You could also have a POH, where instead of the negative log of H3O plus, we could have the negative log of the OH minus ion concentration instead. In pure water, if we took the negative log of 1 times 10 to the minus 7th, that would equal 7. So your H3O plus would be 1 times 10 to the minus 7th. Your OH minus would be 1 times 10 to the minus 7th. So your pH would also equal your POH at that point, and both would be equal to 7. If we have a acidic solution, the acid will have a higher H3O plus concentration than pure water, so its pH will be less than 7. When we have a base, we have a lower H3O plus concentration than pure water, so it's going to have a pH that would be greater than 7 as well. The pH scale basically runs from 0 to 14. However, we can have it go above 14 and below 0 for those more concentrated solutions. I gave you a little flow chart last year that you could follow to help you with all the calculations. You can look for this, just comparing your H3O plus and your OH minus concentrations. You can take the Kw, which again at 25 degrees Celsius, which is our standard temperature, 1 times 10 to the minus 14th, and you can divide one or the other, or divide the Kw by one or the other and solve for the other solution. When we have the H3O plus being greater than the OH minus, again, that's an acidic solution, so we would find that the Kw divided by the H3O plus would give us an OH minus concentration that would be less than 1 times 10 to the negative 7th power. So just as an example, if I told you that we had a acid solution that was 5 times 10 to the minus 3rd power, I could simply take the 1 times 10 to the negative 14th, I could divide it by 5.0 times 10 to the negative 3rd, and when we would get our answer to that, we would have 2.0 times 10 to the negative 12th molar OH minus. So again, my H3O plus would be greater than my OH minus, which would make it an acidic solution. So here's where we can now start to look at our relationship between pH, pOH, and the pKw. So we had our equation for the autoionization of water, Kw equals H3O plus times OH minus equals 1 times 10 to the negative 14th. So what we can do here to make it a little bit easier on ourselves, use our properties of logarithms here. And so if I took the negative log of the entire equation, the Kw equals the H3O plus times the OH minus. You'll remember with your properties of logs that when you do your logs, you would add them together. So in this situation, I have the pKw, which again, negative log of 1.0 times 10 to the negative 14th. That would equal 14. So I'd have 14. By definition, we would have that being equal to the negative log of the H3O plus the negative log of the OH minus. So when we look at this, we know that the negative log of the H3O plus is the pH. The negative log of OH minus, that is the pOH. So we have an equation that we can use to go in between. 14 equals the pH plus the pOH. Again, we can use that with the pKw for any aqueous solution at any temperature. It doesn't have to be 25, but it will always be 14 at 25 degrees Celsius. Kw, again, is a constant at the constant temperature, so the values of the pH, the pOH, H3O plus, and OH minus are all interconnected. So you had that little flow chart that I showed you guys last year where you could have the H3O plus, the OH minus, you could have the pH, and you could have the pOH. So again, either of these two equations, you could have 14 equals the pH, and you would subtract the pH here. So 14 minus the pH equals the pOH, and 14 minus the pOH equals the pH for the one going down below. For the H3O plus and the pH relationship, if we're going from the pH to the H3O plus, we're taking 10 and we're raising it to the negative value of the pH, and then we have the negative log of the H3O plus concentration for the pH calculation. Same thing on the other side. I could have 10 to the negative pOH to go from the pOH to the OH minus concentration, or I could take the negative log of OH minus going from OH to the pOH. And then finally, going in either direction here, if I'm going from H3O plus to OH minus, I'd take the Kw and divide it by the H3O plus. And if I was going from OH minus to H3O plus, I'd take the Kw and divide it by the OH minus concentration. So sorry, that's a little small there, but there you have it. We can now look at the relationship between the H3O plus, the pH, pOH, and the OH minus ion concentrations. So when we are looking at the solutions in terms of the H3O plus concentrations, again, it's neutral at 1 times 10 to the minus 7th, so anything greater than that would be an acidic solution. Anything less than that would be a basic solution. You can see here what I was referencing before. If I have a 10 molar concentration, I'd have a -1 for the pH. Negative log of 10 would be a -1. If I had a 1 molar concentration, that would give us 0. Conversely, if I had an OH minus concentration that was 10 molar, then I would have a pH of 15 instead. Once you get to the 15, it's pretty hard to go much higher, and it is pretty hard to go lower than a -1. It can happen, but not very readily before that solution becomes saturated for the H3O plus concentration and cannot increase anymore. Same type of thing. You'll notice here with my OH minus concentrations, now we're just kind of flipping it. If I have a larger concentration than 10 to the -7th, then it's a basic solution. And as I get less than 10 to the -7th, it becomes acidic. You'll notice that my pOH scale is flipped, where I have now the most basic having the -1 and the most acidic solution having the 15. Notice, however, though, that relationship still holds true. 14 equals pH plus pOH. So you'll notice I have -1 and 15. They still add up to 14. 14 and 0, 13 and 1, 10 and 4. All of them will add up to equal 14. Okay, so now we're going to start to look at calculating some pHs. So in this first instance here, I have the negative log of 1 times 10 to the -4th. Now, when we talk sig figs, we want to focus on the number out in front, and that would have 2 significant figures. The number that we see in the front of the decimal for the pH is going to be a non-significant digit. It's only the number of digits that are after the decimal point that matter. Because if you think about it, this one here is not significant because it's just showing us the placement of the decimal. So therefore, this number here, when we look at the pH, and it would be 4.00. This number is corresponding to the exponent that we see, and that is just a placeholder. So therefore, the only numbers that count are the ones in front. Since this has two significant digits, 1.0, I would have two numbers after the decimal point. It's a little counterintuitive at first, but because we're using numbers in scientific notation, that's what we have to do. So 4.00 would be the correct answer. If I look at the next one, now notice I have OH minus. So if I take the negative log of 0.04, that will tell me the POH. And if I do that with its two significant figures, I end up with 1.40. But that again is the POH. So I would take 14 minus the POH equals the pH. So 14 minus 1.40. The 14 has an unlimited number of significant digits. So my final answer will be 12.60. Okay, so for this next example problem, we have a pH for a solution given as 5.85. So it is asking us to determine what the concentrations of H plus and OH minus are for this solution. So again, just as a quick little reminder, since the pH is less than 7, I know that that would mean that I have an acidic solution. So I should expect that my H plus concentration should be greater than my OH concentration once completed. So as we start this problem off, again, to determine the H plus or the H3O plus concentration, I'd take 10 and raise it to the negative pH value. So in this particular instance, if I take the second log of a negative 5.85, we end up with 1.41 times 10 to the negative 6th molar H3O plus. So you have a couple different options to solve for the OH minus. It will give you the exact same answer either way, but you can either use the KW and divide by the H3O plus concentration that is given to solve for the OH minus, or the other thing that we could do would be to simply take 10 to the negative POH and just use 14 minus the 5.85 for, again, the pH equals the POH. So if I do that, I'd end up with 8.15 for my value of the POH, and I could now take 10 to the negative 8.15 to equal the OH minus concentration. So if we do that, we end up with 7.08 times 10 to the negative 9th power. So I want to start getting you guys to think about the types of solutions that you are creating. So the first thing that you always want to do is identify what the major species are in solution, and namely, is the acid or a base that we are looking at a strong acid or a strong base? Because that's going to determine what type of math we have to do in order to determine the pH of the solution. So when we look at this, because I have HCl here, I know that the HCl is a strong acid. So therefore, I know that the HCl will react with the H2O, forming H3O plus and Cl minus. And excuse me, that should be a single arrow. So in this case, strong acid, it is going to be going almost to completion. So we know that the HCl concentration initially will be approximately the same thing as the H3O plus concentration in the solution. So my major species that are in the solution, I would have the H2O, I would have the H3O plus, and I would have the Cl minus. Again, I leave off the HCl because it's going to completely dissociate. And so there will be very little to none that would be left in the solution. So now, because I know the HCl and the H3O plus concentrations are essentially the same, then I can say that I have an H3O plus concentration equal to 2.0 times 10 to the minus third. Notice again, I have two significant figures for my answer, so I'm going to have two numbers after the decimal point. So if I plug in to solve for the pH, take the negative log of 2 times 10 to the minus third, and we end up negative log 2.0 times 10 to the minus third. We end up with 2.70. It's 2.6989. So we can round that up to two significant figures. Again, the 7 and the 0, those are the two significant figures. And the 2, again, is insignificant. So again, I'm just going to put a box around it, and just, this will be the last time I do that, but the 2 here is insignificant because that's just showing us the decimal placement for the number. So again, 2.70 would be our pH. For this next problem, we're going to calculate the H3O plus, pH, OH minus, and POH for a 0.0042 molar calcium hydroxide solution at 25 degrees Celsius. The first thing I want to do is identify what the major species is in solution. So I have the CaOH parentheses 2. Remember, that is one of our strong bases. We know that because it's a heavier group 2 metal hydroxide. So now I need to set up a dissociation equation for this solution. So I start off with the CaOH parentheses 2. The significance of this is again the 2-to-1 ratio. I know for every 1 formula unit of the calcium hydroxide, I have 2 ions of hydroxide that will form. So if I would start off with 0.0042 for the molarity of the calcium hydroxide, I'd have 0.0042 for the molarity of the Ca2 plus, and I'd have 2 times the 0.0042, which would equal 0.0084 molar OH minus. So as I mentioned on one of the previous slides, when we're doing these problems and solving for the opposite H3O plus or OH minus, you have a couple of different ways that you can attack it. Since we haven't calculated pH yet, I'm going to go with that other direction and use the Kw equation, where I have the H3O plus times the OH minus equaling the Kw. Kw again, always 1 times 10 to the negative 14th. So I can divide both of those by the OH minus concentration, which was 0.0084, and that will tell me the H3O plus. So I have 0.0084 for the OH minus. I have for the H3O plus 1.2 times 10 to the negative 12th. So now at this point here, I have my molarity for the H3O plus. So I'm ready to go ahead and solve for pH. So for pH, I can take the negative log of 1.2 times 10 to the negative 12th, and that will be 11.92. Again, two significant figures. And the POH, I could do either as 14 minus the 11.92, or I could take the negative log of 0.0084. And in either case, I end up with 2.08. So that is it for this particular problem. Okay, so we're now going to look at solving weak acid equilibria problems. So this is going to be a much different approach than what we had with the strong acid or strong base type problems. The concentration of the H3O plus is not going to be remotely close to the concentration initially for the acid. Remember, by definition, strong acids dissociate 100% completely. Weak acids typically less than 5% will actually dissociate. So we've got to go through and solve for the H3O plus using the equilibria expression for your particular acid. So the first thing, write out your balanced equation for that ionization or dissociation of the acid. Write out your expression for Ka, and then we want to define X as the change in the concentration that we would occur during the reaction. So think about your rice table, and then make assumptions that will simplify the calculation. So again, this part right here is referring to your 5% rule. So once again, just as a part to review, you can look for your changes in your exponents. So I'm just going to put it right here. So your change in the exponents. Remember, if it's greater than 3, no quadratic is necessary. Less than 3, quadratic is necessary. And if it is 3, then we have to check. So now that was one way. A second method that you could do would be to take X, divide it by the initial concentration of your acid, and multiply that by 100%. Okay, so you're changing X divided by the initial concentration. If that again is less than 5%, then we don't have to worry about the quadratic. Above 5% we do. And then there's the one catch-all for this. You can take the initial concentration of your acid and you can divide that by the value for the Ka. And if that is less than 400, no quadratic would be required. If it's going to be less than 400, we would have to do the quadratic. So greater than 400 or equal to 400, or sorry, greater than 400, no quadratic. Less than or equal to 400, you would have to do the quadratic equation. So once you have that, you can then take the value for X as being your concentration of the H3O plus, and then take the negative log of that concentration. So again, as we are looking at these problems, molar concentrations are the brackets. Formula with no subscript indicates an equilibrium concentration. Again, what we're talking about for that is that initial concentration. So if you don't see the not sign, the little 0 underneath it, then it would be a equilibrium concentration and not an initial concentration. So the H3O plus from the autoionization of the water typically will be negligible. So the weak acid has a small Ka and its dissociation would also be negligible. So your initial concentration for the acid will typically be its equilibrium concentration as well. So again, that is making the assumption of the 5% rule. So don't have to do the minus X in most cases. Okay, so for this, let's just start off by identifying what are going to be the major species in the solution if I have a weak acid, hydrocyanic acid, that is being mixed with water. So I have a 0.80 molar aqueous solution. Notice here the Ka is given 6.2 times 10 to the minus 10th. So this is what we're talking about. 0.80, we could rewrite that as 8 times 10 to the minus 1. Because this is minus 1 versus minus 10, difference in my exponents, just think of the number line, is 9. So therefore, I know it's going to be very small for the change in X. So in this case, we could say that the HCN concentration initially would be the same as the equilibrium concentration of HCN. As far as what the major species are in solution, you would have again the HCN and the H2O, and it would form just a little tiny bit of the H3O plus and the Cn minus. So my major species in the solution, we would have the HCN and the H2O. Each one of these here, I'd have the 0.8 molar approximately at equilibrium here. And then on the other side, you're talking about somewhere approximately around 10 to the negative 6th for the molarity of the H3O plus and the Cn minus. As a result of that, because it is so small, the major players would be the HCN and the H2O. Okay, so now let's look at a sample Ka problem. This is asking us to solve for the pH of a 0.0200 molar aqueous solution of HF. The Ka of HF is 6.8 times 10 to the minus 4th. So the first thing I want to do is set up my equation. So I have HF plus H2O forming H3O plus and F minus. I'm given an initial concentration of 0.0200, and I would have 0 and 0 for the concentration of H plus and O and F minus. I'd have minus X plus X plus X. So at equilibrium, I'd have 0.0200 minus X, X, and X. So my Ka expression would be H3O plus times F minus over concentration of HF. So the first thing I want to do is make my assumption and see. So when I look at this, this would be 10 to the negative 2. This would be 10 to the negative 4. So once again, that one being less than 3, I know that I'm going to have to do the quadratic equation. So at this point, just as a further check, I'm going to take the 0.0200 divided by the 6.8 times 10 to the negative 4th and see what it's equal to, which if we type that in is equal to approximately 29. So I know for a fact as a result, again, less than 400, we're going to unfortunately have to do the quadratic equation. So as I set up my problem here, I have my Ka being, and I'm going to do this down here, 6.8 times 10 to the negative 4th equaling x squared over 0.0200 minus x. So I need to FOIL everything out together, and when I do that, I get 1.36 times 10 to the negative 5th minus 6.8 times 10 to the negative 4th x equals x squared. So when I put everything together on the same side, I have x squared plus 6.8 times 10 to the negative 4th minus 1.36 times 10 to the negative 5th. Now when we do our quadratic equation, my A is 1, my B is 6.8 times 10 to the negative 4th, and my C negative 1.36 times 10 to the negative 5th. If I plug those values into my equation, again, negative B should be negative 6.8. Well, let me put the quadratic here first again, just to remind everybody. So I'd have negative B plus or minus the square root of B squared minus 4AC all over 2A. So I have a negative 6.8 times 10 to the negative 4th plus or minus the square root of 6.8 times 10 to the negative 4th squared minus 4 times 1 times a negative 1.36 times 10 to the negative 5th. And we're going to divide all that by 2. So we have two roots that come from this. The first root that we have is 3.36 times 10 to the negative 3rd. Or my second root is negative 4.04 times 10 to the negative 3rd molar as well. So in this situation here, again, because I have a negative root, I know that I can automatically cancel that off. So my x value is 3.36 times 10 to the negative 3rd. And now to solve for the pH, because my x is defining the H3O plus, so this value here would be my x up top. I can now take the negative log of the 0.00363, and our pH for that solution would be equal to 2.44. Okay, and actually I take that back. I need to add one more 0 for 3 significant figures. So 2.440 with 3 significant figures. Now, just as a point of reference, If it happened to ask us for the HF concentration, I could then take the 0.02 minus the 0.00363, and we'd have a final concentration of 0.01637. So we could plug that in. If we did this here, we'd have 0.01637, and that would be somewhere roughly around 18% for the dissociation of this. So again, to figure that out, again, you could see the change in X over the initial concentration and solve. So not going to do that for us, doesn't really matter in this case, but we would have somewhere in that vicinity here of that. So now let's look at our last problem, which is going to be an example KB problem. It's going to be the same type of concept here, except our initial equation is going to be different. I know that the NH3, that is a weak base. Anytime you have an amine, some type of NH group that's attached to some hydrocarbon, it's going to be a weak base. So again, in this situation, because it is a weak base, I know that I'm going to be solving for OH minus instead of H plus. So same type of concept to begin with. Write the equation out. So I have NH3 plus the H2O, forming in this case NH4 plus. I know that the NH3, because it is the base, is going to accept a proton. So the hydrogen is going to give from the water to the ammonia to form the NH4 plus, and that would leave us with OH minus as the other product. Setting up my rice table, again, I would have 0.100, 0, and 0, minus X, plus X, plus X, and now I'd have 0.100 minus X, X, and X. My KB expression, I would have for this the NH4 plus concentration times the OH minus over the concentration of NH3. And now doing our quick little 5% check over here, I can take my initial concentration, 0.1, and divide it by 1.8 times 10 to the negative fifth, which would be my KB, and 0.1 divided by 1.8 times 10 to the negative fifth, that would give me 5,556. So since it's greater than 400, this would be one of the easy ones where no quadratic would be necessary. So we can make the assumption that X is going to be close to 0. So I can just simply say 1.8 times 10 to the negative fifth equals X squared over 0.1. So now multiply both sides by 0.1. And that gives us 1.8 times 10 to the negative fifth, times 10 to the negative 6, equals X squared. And then I can take the square root of that, and my X would equal 1.34 times 10 to the negative third. So now that tells me my OH minus concentration. So I can solve for POH by taking the negative log of X. Since you've already defined what the value for X is, don't waste the time writing it out. You can just say negative log of X here and just plug in and solve. I need, let's see, 3 significant figures again. So I would have, actually I guess I can have 2 because of the 1.8. I take that back. So we can do the negative log of that, and that gives us 2.87 for the POH, and I have 14 minus the POH to equal the pH. So 14 minus 2.87, my pH would be equal to 11.13. Okay, so to summarize, when we are discussing acidic solutions, In most of those solutions, the concentration of H plus is going to be quite small. We express the H plus concentration in terms of pH to make it easier for the number to deal with. So pH again is the negative log of H plus or the negative log of H3O plus. Again, this is a logarithmic scale, so we're trying to make the numbers easier for us to use. Thus, a change in the H plus concentration by a factor of 10 causes the pH to change by 1 unit. Most pHs will fall between 0 and 14. In neutral solutions, pH is equal